and then from B to A, and then from A to A dash, all on the fixed wire. This current was also closed. If a similar circuit be exposed to the action of a closed current C, the movable part will be displaced just as if it were acted on by a force. Ampere admits that the force apparently acting on the movable part AB, representing the action of C on the portion beta of the current, remains the same whether an open current runs through beta. Stopping at A and beta, or whether a closed current runs first to beta and then returns to through the fixed portion of the circuit. This hypothesis seemed natural enough, and Ampere innocently assumed it. Nevertheless, the hypothesis is not necessity, for we shall presently see that Helmholtz rejected it. However that may be, it enabled Ampere, although he had never produced an open current, to lay down the laws of the action of a closed current on an open current, or even on an element of current. They are simple. 1. The force acting on an element of current is applied to that element. It is normal to the element and to the magnetic force, and proportional to that component of the magnetic force which is normal to the element. 2. The action of a closed solenoid on an element of current is zero, but the electrodynamic potential has disappeared. That is, when a closed and an open current of constant intensities return to their initial positions, the total work done is not zero. 3. Continuous rotations. The most remarkable electrodynamical experiments are those in which continuous rotations are produced, and which are unipolar induction experiments. A magnet may turn about its axis. A current passes first through a fixed wire, and then enters the magnet by the pole N. For instance, passes through half the magnet, and emerges by a sliding contact and re-enters the fixed wire. The magnet then begins to rotate continuously. This is Faraday's experiment. How is it possible? If it were a question of two circuits of invariable form, C fixed and C' movable about an axis, the latter would never take up a position of continuous rotation. In fact, there is an electrodynamical potential. There must therefore be a position of equilibrium, when the potential is a maximum. Continuous rotations are therefore possible only when the circuit C' is composed of two parts, one fixed and the other movable about an axis, as in the case of Faraday's experiment. Here again, it is convenient to draw a distinction. The passage from the fixed to the movable part, or vice versa, may take place either by simple contact, the same point of movable part remaining constantly in contact with the same point of the fixed part, or by sliding contact, the same point of the movable part coming successively into contact with the different points of the fixed part. It is only in the second case that there can be continuous rotation. This is what then happens. The system tends to take up a position of equilibrium, but when at the point of reaching that position, the sliding contact puts the moving part in contact with a fresh point in the fixed part. It changes the connections and therefore the conditions of equilibrium, so that as the position of equilibrium is ever eluding, so to speak, the system which is trying to reach it, rotation may take place indefinitely. Ampere admits that the action of the circuit on the movable part of C' is the same as if the fixed part of C' did not exist. And therefore, if the current passing through the movable part were an open current, he concluded that the action of a closed on an open current, or vice versa, that of an open current on a fixed current, may give rise to continuous rotation. But this conclusion depends on the hypothesis which I have enunciated, and to which, as I said above, Helmholtz declined to subscribe. 4. Mutual action of two open circuits. As far as the mutual action of two open currents, and in particular that of two elements of current, is concerned, all experiments break down. Ampere falls back on hypothesis. He assumes 1. That the mutual action of two elements reduced to a force acting along the joint. 2. That the action of two closed currents is the resultant of the mutual actions of the different elements, which are the same as if these elements were isolated. The remarkable thing is that here again, Ampere makes two hypotheses without being aware of it. However that may be, these two hypotheses, together with the experiments on closed currents, suffice to determine completely the law of mutual action of the two elements. But then, most of the simple laws we have met in the case of closed currents are no longer true. In the first place, there is no electrodynamical potential, nor was there any, as we have seen in the second case of a closed current acting on an open current. Next, there is, properly speaking, no magnetic force, and we have above defined this force in three different ways. 1. By the action of a magnetic pole. 2. By the director couple, which orientates the magnetic needle. 3. By the action on an element of current. In the case with which we are immediately concerned, not only are these three definitions not in harmony, but each has lost its meaning. 1. A magnetic pole is no longer acted on by a unique force applied to that pole. We have seen, in fact, the action of an element of current on a pole is not applied to the pole but to the element. It may, moreover, be replaced by a force applied to the pole and by a couple. 2. The couple which acts on the magnetic needle is no longer a simple director couple, for its moment with respect to the axis of the needle is not zero. It decomposes into a director couple, properly so called, and a supplementary couple which tends to produce the continuous rotation of which we have spoken above. 3. Finally, the force acting on an element of a current is not normal to that element. In other words, the unity of the magnetic force has disappeared. Let us see in what this unity consists. Two systems which exercise the same action on a magnetic pole will also exercise the same action on an indefinitely small magnetic needle, or on an element of current placed at the point in space at which the pole is. Well, this is true if the two systems only contain closed currents, and according to Ampere, it would not be true if the systems contained open currents. It is sufficient to remark, for instance, that if a magnetic pole is placed at A and an element at B, the direction of the element being in A produced, this element, which will exercise no action on the pole, will exercise an action